Hello everyone, today we're going to be learning about perfect powers in additive number theory, and I have actually a really interesting question for you. It might be a little bit different from what you all have faced till now, and you might be wondering what this additive number theory is, right? And additive number theory is essentially the behavior of certain integers under addition, and it's a part of combinatorial number theory, and it's actually a relatively new field. So a lot of research is being done and will be done in this area. So if you're someone who's interested in research in mathematics, you should definitely try to look in this area. But yeah, let's get back to the problem. And this is the second problem from the Asia Pacific Mathematical Olympiad in 2010. In this video, we're going to be learning about perfect powers in additive number theory, well, the easy case and the general case. After that, we have some book suggestions for the APMO and serial Olympiads, and at the end, we have a continuation of the problem.
This video is sponsored by Cheenta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so they are asking us that for a positive integer k, call an integer a pure kth power if it can be represented as m raised to the power k for some integer m. So for example, m square is a perfect 2th power, it's a perfect square, m3 is a perfect 3th power, it's a perfect cube, and so on. Show that for a positive integer n, there exists n distinct positive integers, so that the sum is a pure 2009th power and the product is a pure 2010th power. Essentially, what we're going to do is we're going to convert this problem into a little bit of algebra. So what they're trying to say is that a1 plus a2 all the way till an, which is the sum, is a perfect 2009th power, and the product a1 a2 all the way till an is a perfect 2010th power, right? And this is obviously holding true for ai comma m1 comma m2 to be natural numbers, so they definitely need to be naturals. So we're going to be looking at the easy case and the general case, like I said, and the general case would be something like this. We can essentially say that sigma ai is equal to m1 raised to the power k, and pi of ai is m2 raised to the power k. And this is just a notation that I'm using. The sum is usually denoted as sigma, and the product is denoted as pi, and m2 raised to the power k plus 1 actually. Sorry about that. So this is the general case, and actually k is equal to 2009 is what they want us to prove in the question, right? K is equal to 2009, and our question will be done. Let's proceed. Let's see how we can proceed. So before kind of like going into the intricacies of the solution, let me first discuss the easy case. And it's really important to know this because this is where kind of the motivation of the problem came from. This is how the problem was constructed, right? So the easy case is nothing where you put k is equal to 2, so k plus 1 is equal to 3, right? And we're going to be setting certain numbers. So let's set b1 is equal to 1 cube, b2 is equal to 2 cube, and all the way up till bn is equal to n cube. And when I do that, and if I calculate the sigma bi, I'll get 1 cube plus 2 cube all the way up till n cube, there exists a very good closed form for this. It is n plus 1 by 2 whole squared. So it's a perfect square, and that's great because that's what we need, right? K is 2. And if I actually calculate pi of bi, pi bi would be nothing but 1 cube times 2 cube all the way up till n cube. So it's n factorial whole cube, and again that's a perfect cube. So this is observation that the sum is a perfect square and the product is a perfect cube. Is I think the reason behind why this problem was formulated in the first place. So once now we are through that, let's come back to the general case. And again, for the general case, I'm going to be again using a little bit of substitution. I'm going to plug in b1 is equal to 1 raised to the power k plus 1, b2 is equal to 2 raised to the power k plus 1, and all the way up till bn is equal to n raised to the power k plus 1. And well, once we do that, we can actually notice a couple of things, right? b1 times b2 all the way up till bn can actually be written as n factorial raised to the power k plus 1. And if I actually calculate the sum b1 plus b2 all the way up till bn, what will it be? 1 raised to the power k plus 1 plus 2 raised to the power k plus 1 all the way up till n raised to the power k plus 1. Now I do know that there exists a closed form for this, but it's very ugly and it's definitely not a perfect kth power. So let me just denote it by x, right? And again, now we're going to be using a little bit of substitution. So a1 is b1 times x raised to the power t, a2 is b2 times x raised to the power t. You might have guessed it, an would be bn times x raised to the power t. And why I did that is when you take the sum, right, if you take the sigma ai, actually x raised power t can be taken as common, and you're really left with sigma bi. So sigma ai is nothing but x raised power t times x, which is x raised power t plus 1. And then you calculate pi of ai. What is pi of ai? Pi of ai is essentially b1 times b2 times b3 all the way up to bn times x raised power nt. So pi of ai is nothing but n factorial raised power k plus 1 times x raised power nt. Right, now this is a little bit of the major portion of the solution. This is kind of where we go on. So, well, what can we write? So pi ai, what was given us in the question, was nothing but m2 raised power k plus 1, which is equal to n factorial raised power k plus 1 times x raised power nt. So if you actually notice that this is a perfect k plus 1th power, this is a k plus 1th power, this also needs to be k plus 1th power. Another observation is that sigma ai, which was x raised power t plus 1, is m1 raised power k. So essentially this t plus 1 needs to be perfect kth power, right? And once we've really done this, we can actually write a couple of things over here, right? What are they? Essentially x raised power t plus 1 is equal to m1 raised power k, so therefore k divides t plus 1. And the other thing that you can notice is since x raised power nt also needs to be a perfect k plus 1th power, therefore we can say that k plus 1 divides nt. Now k plus 1 divides nt for all natural numbers n, so you can essentially write that k plus 1 divides t. And once you've reached till this point, most of your work is done, so let's just kind of wrap it up. So from this is the first equation, this is the second equation. From the first equation I can write that t plus 1 is pk, and I can, from the second one I can write t is q times k plus 1. And if I substitute the value of t into this equation, I'll get q times k plus 1 is equal to pk, and that gives us qk plus q plus 1 is equal to pk, and q plus 1 is equal to k times p minus q. So q is k times p minus q minus 1. So really q is something times k minus 1. Now if you actually see p and q are variables that had been introduced by us. They are kind of intermediaries in the solution, if you want to put it that way. So you can really fiddle around with them a little bit. And I'm going to actually take p minus q to be equal to 1. And when I take that, I get q is equal to k minus 1. And what was t? T was q times k plus 1. Right? So t essentially becomes k squared minus 1. And that's actually great because we are like almost to the end of the solution. And now that we have the value of t, what was sigma ai? Sigma ai was x raised power t plus 1, which becomes x raised power k squared minus 1 plus 1, which becomes x raised power k squared. And sigma ai can then be written as x raised power k whole raised power k. So it's a perfect kth power, which is what we had to prove. Now, if I actually calculate pi ai, that becomes n factorial raised power k plus 1 times xn raised power k squared minus 1. It was x raised power nt, but I just substitute t as k squared minus 1, right, from what we had found. So pi of ai then becomes n factorial raised power k plus 1 times x raised power n times k minus 1 whole raised power k plus 1. I'm trying to formulate a perfect k plus 1 power. So pi ai then becomes n factorial times x raised power n times k minus 1 whole raised to the power k plus 1. So if you actually see, this is also a perfect k plus 1th power. So we've actually proved what we had to prove. We had to prove that sigma ai is a perfect kth power, and sigma and the product ai is a perfect k plus 1th power. This is a perfect k plus 1th power, and the summation is a perfect kth power. So essentially this is what we had to prove. And if you actually plug in k is equal to 2009, you get the solution to the problem. So we've essentially proved that sigma ai is equal to m1 raised to the power 2009, and pi of ai is m2 raised to the power 2010. And that wraps up the solution. Okay, so I hope you learned quite a bit from it. And yeah, so we're going to be moving on to some book suggestions for APM and senior Olympiads, mostly for number theory and algebra. So we have APMO Compendium, obviously a very important resource, Polynomials by Barbeo, Elementary Number Theory by Sierpinski. And of course, if you need any more additional resources, you can definitely go to AOPS, Art of Problem Solving, probably one of the best websites in mathematics for competitive math. And yes, now we have a little bit of a continuation of the problem. So prove that 2009 and 2010 in the previous problem can be replaced by any numbers x, y such that the GCD is 1. Any copulent numbers. And if you actually gone through the video, if you understood this should be extremely trivial. And so I expect quite a few responses. But yeah, if you're able to do this or make any progress on it, let me know in the comment section. And until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit Cheenta.com.